Oh, okay. You're on Zoom already?
Yeah.
Yes.
Test, test. All right. Can people on Zoom hear me? All right. Yay. Sounds good.
It's quiet.
Yeah. No one's around.
Wednesday was hot one today.
It's so quiet.
Today, not options, maybe. Maybe people were like,
3A do.
yeah.
Also, like it's Cal days getting started. Like people are busy with their clubs, if anything, right? Sad. This is like one of my favorite lectures.
This is a good one.
It's a fun one. Yeah.
So goes. We won't have all the Celeste.
Yeah, the Celeste people aren't going to be here this time, I hope. That was funny. Yeah. All right. Let's get started with announcements right now. Good afternoon, everyone. How's everyone doing? All right. Main thing for today. 3A is due tonight. How's everyone going with that? Doing well? Doing well? How many people still have a bit more work to do on that? All right. You think you are ready to finish by tonight? How many people are a bit behind right now? They don't think they can finish by tonight. Just few people. We should have some extensions available, right? Yeah. So hopefully you can get that done soon. Uh, as I said, the more time you the more time you have for 3B, the better the end result is going to be. So you definitely want to take a lot of time to work on this project if you can. All right. Other than that, not much going on in the assignment side. Project three is kind of the focus of the class for this next few days, just because we want to give you as much time as possible to work on that. Yeah. Other than that, we should be getting the final results for the midterm back soon. We're just finishing up regrades requests now. They have closed, so we're just going through them at this point. All right. Before I get started, do you have any questions about anything we've covered so far? All right. So today we're going to be solving effectively one problem. We've seen a lot of these sorting algorithms so far. And you might notice that we keep getting a lot of similar runtimes, right? We always get n log n. We haven't talked yet about stability. We're going to talk about that in the next sorting lecture. But in effect, depending on the sorting algorithm you use, you will have different speeds and different advantages and disadvantages. Most of the time, you'll be using one of quicksort, merge sort, and insertion sort as the simplest three. If you really want to get into it, then there are much more complicated, much faster algorithms, like power sort, which is used by Python internally. Now, sorting tends to be a foundational problem. You tend to use sorting as the first step in a larger problem. It tends to be useful to just put everything in some order. When you're starting with an unordered list, sorting them into some order ends up helping solve another problem. So, for example, if you're trying to find two duplicates in a list, right? If it's an unsorted list, then it takes n squared time to look through everything because you need to compare every single item to every single other item. But if you sort the list first, then that gets you down to n log n. If you're trying to find, for example, three numbers in a list that add up to some value, the naive solution is to just compare or to check all three tuples. That takes n cubed time. But using a sorting algorithm, you can get it down to n squared. I won't explain exactly how to do that. If you're curious, there is a way to do this. And there's a lot of different ways to sort an array, each with interesting trade-offs. But overall, despite all of the different ways we've managed to find ways to sort, we can't really get much better than the things that we've already found. Today, we're going to try to prove that this is actually true, that it is impossible to do better than what we've seen so far. In other words, we'll be looking at how difficult the sorting problem is, irrespective of the algorithm that you use to solve the sorting problem. Now, for today, we'll be only considering comparison sorts. These are sorts which sort a list according to comparison operations. So we need this to be a list of comparables, and we apply the compare to operation, which compares two items and says which one's greater, and the swap operation, which just swaps two items in an array. So this framework allows us to work with any comparable object. We don't have to worry about, oh, we need this to work specifically on strings or only work specifically on integers. It can be any comparable in this case. So just as a quick knowledge check, can anyone list out any sorting algorithms that we've talked about so far and whether they're comparison or non-comparison sorts? Give me an example of a comparison sort. Anyone? Yeah. Yeah, selection sort. Because all it does is compare items. We compare items when finding the minimum, and then we swap items by swapping the smallest to the front. Any others? Huh? You? Huh? Quicksort? Yeah. We saw that quicksort is using only those comparisons and swapping. Anything else? Huh? Yeah, merge sort. Anything else? Yeah. Are they all comparison based? Not all sorts are comparison based. Most of the ones we've covered are. Huh? Yeah, insertion. Any others? Heap sort, yes. Pretty much a lot of the ones that we've covered so far. Anything else? How about some non-comparison sorts? Yeah. BOGO sort. Now, this one's kind of weird. It's kind of a bit non-comparison because you do use randomness. You do also need to do comparisons to check if it's in sorted order and you do swap items. So it is kind of iffy. It depends on whether you classify the randomness as inherent to the algorithm and not part of the comparisons, or if you consider it as one of like several types of BOGO sorts, depending on the random number generator. Yeah. Sleep sort. Yes, we didn't cover sleep sort in this class, but in effect, the way that sleep sort works is if you have a list of items, you set a timer of that number of seconds, and then you just wait to hear which one's ranked first. So if you have a list of like 10, 5, and 1, you set a timer of length 10, you set a timer of length 5, you set a timer of length 1, and you just wait to hear from them back. It sorts a list. It works, but it doesn't compare any items. Any other sorting algorithms? It doesn't have to be something we've covered in this class. In the back?
Stalin sort?
Stalin sort. Yes. For those of you who don't know, Stalin sort is you take the list, you destroy any items which are not in sorted order, and by the end, the list is sorted. Yes. Any others? Miracle sort. Step one, have list. Step two, a miracle happens. Step three, it is sorted. Yes. There are some joking, funny sorts in this list here. Any other sorting algorithms you want to add onto this list? These are fun? No? All right. Let's keep going. Here's my list of sorting algorithms. It's largely similar. I did add bubble sort in our comparison sorts, and I did add radix sort and gravity sort. We'll talk about radix sort later. Gravity sort is where you take a list of beads. So if you have 10, 5, 1, you get 10 beads, you get 5 beads, you get 1 bead, and then you just kind of shift it this way, shake it, and it's going to fall into order 1, 5, 10. It's kind of weird to think about, but it actually works surprisingly well. Now, we're only going to talk about comparison sorts for today. But before we talk about comparison sorts, I want to start off with just a quick math problem. Let me give you two functions, n factorial and n over 2 to the n over 2. And I want you to prove that n factorial is omega of n over 2 to the n over 2. So prove that n factorial grows at least as fast as this function n over 2 to the power of n over 2. And let's take a few minutes to come up with that proof. I'll give you until, let's say, 2 minutes for this. Another one that I love is intimidation. Step two,
So I think that's the same thing. You just check. When I saw it on this, I just checked over and over. Probably doesn't use it.
It's adaptive. It's faster.
But it is sort of.
All right. Let's have last thoughts. Bring everyone back. All right. Let's bring everyone back. Did anyone have a proof of this statement? Yeah.
Start from n, n times n minus 1 times n minus 2. You need to subtract 1 n over 2 times to get to n over 2. So you have n over 2 numbers that are bigger than n over 2. And on the right side, you have n over 2, n over 2. So you're already bigger than that set. You also have things that are smaller than 1.
Yep. That sounds like a good way to prove it. It's very similar to the way that I was going to say it, right? So let's take a look at an example. If you have 10 factorial here, you have 5 of these items that are greater than n over 2. N over 2 of these are greater than n over 2. So this thing is clearly greater than this. This is greater than this. Each of these is greater than this. And at the very end, you have a bunch of times ones here. This part here is just going to strictly increase the number. So in a way, if you look at this, every single number has a corresponding, every single number in the factorial is greater than a corresponding number in the n over 2 to the n over 2. So you can say that this thing is going to grow faster than this thing. So for sufficiently large n factorial is going to be greater than n over 2 to the n over 2. Any questions on this here? All right. My next question. Now that we know that n factorial is greater than n over 2 to the n over 2, let's show that log n factorial is omega of n log n. Now, we're going to use an unspecified base here. You can imagine it's base 2 or base 10, just any base constant. Let's try to show that this is a true statement. And here are some log rules to remind you. Let's take another few minutes to come up with proof on this. All right, let's bring everyone back. What did people say? Did anyone have a proof of this? Yeah. Yeah, that sounds reasonable. Yeah. So here are the steps. I'm going to start off. We know that n factorial is greater than n over 2 to the n over 2 because we proved that in a previous step. I'm going to take the log on both sides. So now we have log n factorial is greater than log of n over 2 to the n over 2. Using my log rules, I can move this n over 2 out. And then using my other log rules, I can split this log into log n minus log 2. Now I can get rid of some unnecessary constants. You can get omega n log n over 2, which is also just the same as n log n. So overall, log n factorial is indeed omega of n log n. So log n factorial will grow at least as fast as n log n. Now, one final question. We've shown that log n factorial is omega of n log n. Now let's show the opposite, that n log n is omega of log n factorial. And let's take another 2 minutes to solve this problem.
You know that.
All right. Let's bring everyone back. All right. What do people think? Someone new. Yeah, let's go for you. Mm-hmm. Mm-hmm. Yeah, that sounds like a reasonable way to explain it. So log n factorial is just log n plus log n minus 1 plus log n minus 2 all the way down to plus 1. How many of these terms exist? N of them. Each one is going to be less than their corresponding term in the n log n, because n log n is just log n plus log n repeated n times. So that means n log n is going to be greater than this log n factorial. So n log n is omega of log n factorial. So given that we know these two things, n log n is omega log n factorial, and log n factorial is omega n log n, what can we actually say now? Let's take a minute, and then I'll pull the audience. Okay. Let's bring everyone back just for the interest of time. How many people say A, n log n is theta of log n factorial? How many people say B, log n factorial is theta and log n? How many people say C, both of these are true? How many people say D, neither of them are true? Yep. Seems like most people are agreeing. Both of these statements are true. Yes, because if function f is omega of g and g is omega of f, then they're both theta of each other. The informal statement where we use something is less than or greater than or equal to, if A is less than or equal to B and B is less than or equal to A, then that means A and B must be the same value. So informally, n log n is theta of log n factorial. They grow at the exact same rate. Now, store that in your brains for now. We are going to come back to this. It is going to appear mysteriously later in this video, or in this lecture. Let's move on to like our main topic for today, trying to find optimal sorting algorithms. So we've shown a lot of sorts that require theta and log n worst case time. one person might ask if it's possible to build a better sorting algorithm. So let's try doing that. We're going to say that this ultimate comparison sort is the asymptotically fastest comparison sort that's possible. It might not even be discovered yet. We might not even know it exists. But we're going to try to prove some things about its runtime. Even though we don't know what it is going to be exactly, we do know some pieces of information about what it could possibly be. For now, I want you to all brainstorm. Try and come up with the best omega and O bounds for the runtime of this best possible sorting algorithm. So this is going to have the best runtime in the worst case. So try and give as good bounds as you can. And let's take a few minutes on this. All right. Let's bring everyone back. All right. Who can give me their bounds? Can you give me an omega bound for this worst case runtime of this ultimate comparison sort? Someone new. Let's see if, yeah. Yeah, omega n is a good one. We do need to look at every single item at least once. Because if you don't look at an item, then you have no idea what its value is. You don't know where it can go. Anyone come up with a better omega bound? Yeah, omega n seems to be a very difficult bound to improve on. How about O bound? Anyone have a good O bound? Yeah.
Sure. It has to be at least omega to start with because we have to like check every element at least once, and then because just checking it once wouldn't sort anything, we would have to have some logic in addition to that. And probably the smallest thing you can do is log in. So I'm guessing you go and log in.
Well, we're looking for an O bound here. So it is going to be true what you said, but that sounds more of an argument for the omega bound, like a lower bound on how slow this gets. I want an upper bound on how slow this runtime is.
Oh, and log in because you need to at least have n, but then like you have to do some sort of logic, which the shortest logic is log in. Otherwise, you're going to take longer.
Well, that sounds again more like an omega proof. Like you're saying that you need to do at least this amount of work. That tells you a lower bound on how much work you need to do. I'm looking for an upper bound. Yeah, this ultimate comparison sort, it's got to be better than at least the same as the ones that we've already come up with. So the worst case runtime is at the very least going to be O of n log n, because we said that this ultimate comparison sort is the best possible sorting algorithm, and we already know merge sort exists. Merge sort is not going to be better than the best possible algorithm. It's going to be worse or equal to. So it's going to be O of n log n at most. And on the other side, first off, I did say initially that it's just omega of 1. Omega 1 because like every function needs to take at least some amount of time to run. The problem doesn't get easier when you increase the size of the list. So you did mention that omega of n is also possible bound. And that's a good reasoning too. You have to at least look at every single item. So far, we know that this ultimate comparison sort, the best possible comparison sort, it's got to be somewhere between n log n and n. Now, that's a fairly small bound, actually. There's not too many functions in between here. But we can do better. We're going to try to show today that the omega bound is actually n log n. We'll need some clever argument to prove this. But once we get this, that means that no matter what algorithm you come up with, if it sorts a list, then it is guaranteed to run in theta n log n, at least. Its worst case is going to be omega of n log n, no matter what algorithm you come up with. And that kind of means that we've already found provably the best possible algorithm to sort a list. Now, the argument's a bit complicated. So let's first start off with an analogy. This is kind of a classic puzzle. Let's say that you have 9 coins, all right? And all of these coins, they're identical in appearance and weight. You can't tell the difference between any of them. But one of them is a counterfeit. That counterfeit weighs slightly more than the other 8, but you can't perceive that directly. What you do have is a precision scale, where you can put 2 sets of coins down on either side, and it'll tell you which side is heavier, or if they're equal. The unfortunate thing is you're only allowed to use this scale twice. So how can you determine which coin is the counterfeit? And I want to guarantee that you can find the counterfeit coin. You can't have a probabilistic algorithm. I want you to guarantee that you'll find the counterfeit. Let's take a few minutes to come up with an algorithm on this.
No, the problem says they're identical in appearance and weight. So I would consider them anyway. That's true. Yeah. I know what you meant to say.
Yeah.
And you can add 8, which I'm gonna think about this. That makes sense.
Yeah.
I'm gonna take away 4 points. It's like, I don't think it's gonna help. The first thing about it is you only get to put 1 on. It's like, that's gonna be hard. That's not right.
All right. In the interest of time, let's bring everyone back. All right, let's bring everyone back. Has anyone come up with an algorithm to solve this problem? Yes, you in the back. All right, you put 4 coins on one side, you put 4 coins on the other. If they're equal, then that means that the last coin is the counterfeit. Yeah. What happens if 1, 2, 3, 4 is heavier? Let's say.
Then you do 2, and then there has to be one of them.
Yes. So if you put 1, 2, and 3, 4, let's say 1, 2 is heavier. You've used up your 2 weighings. You don't know which one's the heavier coin. Any other solutions? You in the back?
Same idea, do 3, 3, 3. So like, you know that the 3 you don't use in the first one. Sorry, if it's equal after the first try, then it's in the 3 that you didn't weigh, and you just progressively do 1 point and 1 point again.
Yeah. So if you start off 1, 2, 3 with 4, 5, 6, if they're equal, then that means the heavy coin is in 7, 8, 9. If they're unweighted, then that means that the 1, 2, 3 has the heavy coin. Either way, you have 3 coins left over, and then you split it into 1, 1, and then look at the last one. Yeah. Here's there's a lot of different solutions, but the classic one is this. You compare 1, 2, 3 versus 4, 5, 6, and there's 3 possible cases. Either the left side's heavier, the right side's heavier, or they're equal. If the left side's heavier, then that means coin 1 is the counterfeit. If the right side's heavier, then that means coin 2 is the counterfeit. If they're equal, then coin 3 is the counterfeit. In the case that the heavier coin is one of these 3. Similarly, for case 2, in case 2, we know that the heavy coin is amongst 4, 5, and 6. So we can do something similar, compare 4 and 5. And then in case 3, where we started with equality, then we know the heavier coin is between 7, 8, and 9. So we can compare 7 and 8 and figure out exactly which one is the heaviest. Here's kind of the full decision tree for the 9 coins. So we start off with 1, 2, 3 versus 4, 5, 6. And then if we say that 1, 2, 3 is greater, heavier, then we go down this left path. And then if you follow down this path, then that tells you which questions to ask and what the results should be for each one. Now, to verify that the scheme works, let's try to check every single case that exists. There are 9 different universes that could possibly exist in this world, right? We could be in the universe where coin 1 was the heavy one. We could be in the universe where coin 2 was the heavy one, and so on. There are 9 total of these universes. And at the start, before we do any weighings, we're kind of in all universes at once. We're in a quantum superposition of all of them because we don't know exactly which one we're in. Every single one is possible. But if we're in universe 1, then we can see that we're going to get the right answer. 1, 2, 3, when we compare 1, 2, 3 versus 4, 5, 6, then it is going to show heavier. When you compare 1 versus 2, it is going to show that 1 is the fake coin. And we've come to the right conclusion. This decision tree does work for this. If we keep doing that for every single one of these, then we end up showing that in every single universe, we get the right result. We get the statement that the particular coin that is the counterfeit is actually the fake coin. Now, I want to ask this question. Is it possible, instead of starting with 9 coins, what if we started with 10 coins? Can we still solve this problem? I see someone shaking their heads. Can anyone give me a reason why it's impossible to solve this problem in this case? Yeah.
Kind of the same situation, like when I try to prepare the workloads on those things, there's always going to be some like
yeah. Regardless of how you set this up, you are going to end up in a case where there's too many choices. Formally, here's kind of what I like to think about it. If you have a 2-layer decision tree, right, it's going to look something like this. Every single decision is going to be either heavier, equal, or greater. So that means that this is the maximum possible decision tree that could exist. And there's only 9 of these leaves at the bottom, right? There's only 9 different answers you could possibly give at the end of this tree. But there's 10 different universes. There's 10 distinct things you could possibly answer. You could say 1 is heavier, 2 is heavier, 3 is heavier, all the way down to 10 is heavier. So that means that by pigeonhole, at least one of these leaves is going to end up having 2 universes in it. And in that leaf, regardless of which one you pick, it is going to have 2 universes go down it. And that means you're going to be wrong at least half the time there. Regardless of which 2 you end up going down, you're going to end up having an incorrect result in at least one of these cases. So it is impossible to solve this problem if you start with 10 coins and use only 2 weighings. Now, if you look at this, each weighing, you triple the number of cases you can manage because every single decision splits the tree down into 3 further values. So with n weighings, you can have at most 3 to the n leaves in our decision tree. So if you have 3 weighings, you can have at most 27 coins. In other words, if you have more than that number of coins, then we've basically proven that no algorithm exists that will solve the problem. So if I gave you 4 weighings and I asked you to solve 100 coins, you can immediately say that this is impossible because 100 is greater than 3 to the 4th, which is 81. Now, does this converse hold true? Can we say that if I gave you n weighings, then you can solve this problem for any 3 to the n or smaller? Well, in this case, it's true. In this particular problem, it is true that if I give you 5 weighings, you will have 3 to the 5 points as your maximum. But it isn't actually true in general. The converse won't always hold. I have some skipped slides that show an example of when this universe bound is fulfilled, but you still can't solve the problem. So this tells you a necessary but not a sufficient condition to show that something is possible. In general, if you have a decision tree that has k layers and a branching factor of r, then you'll have at most r to the k leaves, which means that it can solve a problem with up to r to the power of k distinct universes, assuming each universe yields a different expected return value. If you flip this around, that means that if you have an algorithm that is expected to return up to r to the k distinct results, depending on what its input is, then its decision tree must have at least k layers, which means that if you have a problem with containing k distinct universes, then that decision tree must have omega of log k layers. It takes at least log k steps to come to one of those distinct universes. Now, let's use that to solve a slightly less arbitrary problem. Let's say that we have a puppy, a cat, and a dog. Each of these are in their own opaque boxes. You can't look into them. They're labeled A, B, and C. At the same time, we still have the same scale, so we can compare 2 of these boxes. However, unlike before, you can only compare 2 at a time. You can't put a cat box on top of a puppy box. Sorry. And you will never get equality. All these animals are different weights, so you'll only get a branching factor of 2. Our goal is to write ABC in order of their weights. Given what we've discussed so far, given the fact that the number of universes in this problem needs to be, or ends up bounding the number of decisions you need, what do you think the minimum decision tree height is going to be for this game of puppy, cat, dog? Let's take 2 minutes to solve this problem.
Basically, you have like, I think questions.
Yeah, I always forget. There's like these. Yeah, right. Yeah. I always forget. It's very possible. Was it supposed to animate more than that? No. Yeah, I just copied all of the slide from the Oh, absolute balance. Some of All right, let's bring everyone back. How many people say the answer is A? We need at least 3 steps. All right, how many people say the answer is B? We need at least 4 steps. 5 steps? 6 steps? All right, for those of you who said 3 steps, why is that the case? Why do you say 3? Let's have someone new. I think you're new, right? No, you spoke before. Today. Yeah. You're just, yeah, you're not raising your hand. Sure. Mhm. Yeah, so you came up with an explicit algorithm on how to solve this problem in 3 steps. That's a good way. Anyone else prove this a different way? Yeah.
There are 3 factorial possible reordering that could be like in your universe idea, and then you can't have equality like we had in the case. So there like has to be 2 to the end of your decision tree. So we need 8, which is 3.
Yeah. So solving it, giving an explicit solution is a perfectly valid solution. But it doesn't generalize well when we're talking about like a really large number of these boxes, because I don't want to come up with a new algorithm for every single case. What you said is more generalizable. If you start off with 3 different items, then there's 3 factorial equals 6 different ways you can order these. And if you start with 6 different permutations, then we need a binary tree with at least 6 leaves. This is a binary tree because we always get less than or greater than. So our decision tree needs to have at least 3 layers. Otherwise, we don't have enough leaves. In practice, here is the full decision tree for puppy, cat, dog. We start off by comparing if A is less than B, depending on the answer. If it's yes, then we go down to this. If that's yes, then we know it's A, B, C. Otherwise, we can just keep going down, and so on and so forth. In any case, the most number of steps is 3 in any of these paths. And we can see here that every single one of the 6 permutations has its own distinct leaf. I think this is similar to the approach that you were trying to solve, right? Yeah. Now, what if you wanted to definitively solve the generalized problem? Puppy, cat, dog, walrus, I don't know, horse? Give me another like animal. Elephant, sure. Puppy, cat, dog, horse, walrus, elephant. If you had n items, what would be your omega bound for the amount of time it takes to solve this problem? Anyone want to shout it out? Yeah. Log n factorial? Why?
N factorial means you get the log of that. Right?
Yep. There's n factorial different ways to order this list of items. So we will need at least ceiling of log base 2 n factorial, which is just omega of log n factorial. Now, we don't know for certain that this is a possibility, that it is possible to attain this. So this is just an omega bound. It's a lower bound on the minimum number of steps. But it is a good enough bound for now. Omega of log n factorial is kind of the fewest number of layers we need in the worst case. Now, apparently we used monkey, walrus, elephant in this example, but the optimal decision tree isn't actually known for a lot of different values. We do know the best values for n equals 1 through 15 and 22. We don't know the values for any other numbers. I have no idea why 22 is all of a sudden easier than 16 through 21, but it somehow was. Deriving a sequence of yes-no answers to solve this problem in general is actually surprisingly hard. Because you need to come up with like a ton of different cases. Once you hit 16, there's already 16 factorial different leaves, and you need to come up with 16 factorial minus 1 different questions you should ask. That's too complicated. Instead, what we could do is we could solve this puppy cat dog problem using a sorting algorithm. And here, let me show you how. I'm going to arrange the boxes in a row from A to Z. All right. And then I'm going to create a box class that implements comparable. When I do compare to, then I'll use the scale to compare the different results, the given boxes, and return the result. And for the swap method, I just swap the 2 boxes in my array. Once I sort this array, that'll reorder the boxes from lightest to heaviest, which means I can read out the letters on the boxes from lightest to heaviest. Why do I do this? Well, if I do this, then that means that this puppy cat dog problem, it can be solved using any sorting algorithm I come up with. the ultimate comparison sort, this theoretically optimal comparison sort that I came up with, that one is going to be able to solve puppy cat dog, which means that if I can say puppy cat dog must be solved in omega of log n factorial steps, then that means the sorting algorithm must also run in omega log n factorial steps. Otherwise, we found a way to beat our ultimate best possible runtime for puppy cat dog. Here's kind of a physics analogy. Regardless of how you do it, getting up a hill is going to take some amount of energy. If you can walk, then that means that that walking takes at least that much energy, because from physics reasons, we've increased our potential energy by our mass times the gravity times the height of the hill. At least that amount of energy needs to have been expended in order to walk up. Otherwise, we violate the rules of physics. So if puppy cat dog is a lower bound on our sorting algorithm, that means that our sorting algorithm ends up taking at least omega log n factorial comparisons in the worst case, regardless of what sorting algorithm we come up with. In other words, every sorting algorithm we come up with is omega of log n factorial, because each comparison needs to take at least some constant amount of time. So we've improved our bounds. So how does log n factorial compare to n log n? Everyone? It's equal. We proved already that log n factorial is the same as n log n, which means that the ultimate comparison sort is omega of n log n. Every comparison-based sort is going to require at least n log n distinct comparisons in the worst case. Here's kind of the overall proof summary. It's effectively the same thing that we've been discussing so far. We start off with puppy cat dog. It requires log n factorial comparisons. The ultimate comparison sort solves this problem, so it needs to take at least log n factorial, and that's just the same as n log n. Here's overall a list of all the sorts. And based on what we've said, that means that the ultimate comparison sort is going to be theta n log n. Our best sorting algorithms have achieved that. We have already hit the best possible sorting algorithms, and it is mathematically impossible to do better. We've proven that these are the best possible ones. So there's no point looking for a better one. We are always going to get n log n runtime. Until tomorrow, where we're going to be proving that we can get actually theta n time sorting algorithms. Now, it's not impossible. That just means that we can't use comparison sorts. If we're trying to use comparisons, then we're stuck at n log n, but we can still get better. Now, before I let you go, I kind of want to go over just some fun stuff. There are these sorting videos where you get to watch a list of items get sorted, and it's always just fun to watch these. So let's take a look at one of these.
Sounds like we're doing it Monday.
Hang on, CBS wants to talk. All right, so this video, it has a ton of sorting algorithms, and by a ton, I mean a lot of them. Which one do you want to watch? All right, let's start off with a nice one. I'm going to do Bogo sort last. This one does not have Stalin sort, sorry.
Well, they might need to pick it up next time.
All right, just let's do a quick one. Bubble sort. Let's just watch this one. So you can see the items just move inward. And that's bubble sort. You can see that the items get moved onto the left side earlier. You can also see some other ones. I'm going to do just one more because we're out of time. Let's do max heap sort. Here's the heapification. And then you can see the heap items go down inward as it goes. As the heap steadily falls. Yeah, there is an hour of this, and you can definitely spend just an hour watching all of these sorting algorithms. All right.
Well, not hot enough for Christmas, but since last time I was about 60, it'll be
Wait, we found 16, 17, and 18? Nice. Yay.
disproving a conjecture.
That was just Bogo sort. All right, let's get out.
You're a